Okay, our next speaker is Chenggang Zhang. He's a final year Doctor of Philosophy student at the Engineering Science at the University of Oxford. His research interests include networking and network computing and machine learning. A primary focus of his is in network machine learning and its application to a range of applications, from cybersecurity to financial transactions, and he's currently on the job market.
Yep. Thanks for the introduction. And hello, everyone. Today I'm presenting our work on rapid prototyping of in-network machine learning inference. And let's start with what is in-network machine learning. So in-network machine learning refers to the offload of machine learning inference task to the network device. And it is a type of resource-constrained machine learning that runs within the data plane of the network devices. And unlike other resource-constrained machine learning, you can't just compile the code and run it on a network device. As its pipeline architecture, mainly piece architecture, is very different from a CPU or a GPU. And one may wondering why bother using in-network machine learning given all the existing solutions. And the motivation is what we call the 3 L's. And the first L is location. There are always network devices along the path from a data source to the cloud. In-flight processing, therefore, makes sense. And the network devices aggregate data from multiple sources and allowing better observability than on an end device. And the best is these devices are already part of the infrastructure and do not require extra space or power. The second L is latency. Terminating data on a network device along the path to the cloud will always have lower latency than processed in the cloud. Therefore, in-network machine learning can reduce latency. And the last L is for load. Network switches can process and classify billions of transactions per second, and transactions that no longer go to servers, therefore reduce the load. The last 5 years have seen quite a lot of works on in-network machine learning, but most of these works mainly focus on mapping a single model to a single device for a single application. To make in-network machine learning practical, a rapid prototyping solution is required. This solution needs to support easy configuration and modification of deployed models and easy migration among platforms and use cases. To further explain this point, we studied the line of code that is required to change if you change a single model on if you change a single parameter on a deployed model. And this number can be hundreds of lines in the control plane. And for example, if you use random forest, and also more than hundreds of lines in the data plane. And such a manual modification is both time-consuming and prone to errors. But rapid prototyping is not enough. There also needs to be a general way to match a large number of machine learning models to the data plane, and doing so efficiently so that the mapped model is able to fit within unmodified commodity hardware. So to realize these 2 goals, we introduced Planter. Planter takes a use case from a training data set all the way to a deployment on a target with a single click. For example, given a data set, Planter trains a machine learning model using standard libraries like scikit-learn or PyTorch or TensorFlow. And its front end enables auto-tuning. The trained model is mapped to the P4-based data plane code and control plane code, typically in Python and P4 runtime, including match action table entries. And it also auto-generates bash scripts and code for testing. And after that, it will just compile the code and load the model to the target and test it. Ideally, in-network machine learning should run across a range of different programmable network platforms, from high-end switch ASICs through DPU, smart NICs, and FPGAs to cheap, low-end devices like Raspberry Pi. And Planter support in-network machine learning across all these targets and allow easy migration between platforms. To realize the in-network machine learning, we define 3 methodologies. And the first one, direct mapping, is suitable for sequential algorithms where its workflow matches the pizza architecture. For example, a decision tree where each logical stage is a split in the tree. And the second methodology in code base slice the feature space and assign a code for each slice. And this constructed code allows to achieve a final decision at the end of the pipeline. And it matches algorithm, for example, tree-based algorithm and k-means well. And this methodology allows high table parallelization and thereby enabling good scalability. And the last methodology, lookup-based, look up the result of computations within migration tables and using some smart transformations. And it's suitable for algorithms like SVM and knife Bayes and others. And using these 3 methodologies, Planter support about a dozen machine learning models with 50+ different variations. Planter has a modular framework. It's a modular framework that separates machine learning models, P for architectures, targets, use cases, and others. And this means that the user can just pick the right model, architecture, platform, and the use case, and Planter just take all these parts and turns it into a single program. And also because Planter is modular, it is easy to extend it with new models, platform, and use cases. And the P4 code generated by Planter has 3 components. And the first component is architecture related in purple, creates a program skeleton. And then the use case related component in amber is added. And the last is machine learning related component in red, completes a program, embedding it with user configurations and training results. And Planter achieves high machine learning performance that for most models is similar to run the same size model on a server. And for example, this slide shows the F1 score for anomaly detection use case using the UNSW dataset. And you can see the switch-based model in blue are on par with server-based model in amber. And we also compare with Planter with several state-of-art solutions. And Planter achieves higher F1 score than Clustream, Torus, and Homunculus. And for similar model, requires significantly memory than ED. Well, for all cases, fitting on an unmodified Tofino switch. We also provide further comparisons in our paper. Planter achieves this high machine learning performance without compromising the system performance. And the figure on the left shows the throughput on several Planter-supported targets, and achieving full line rate on Tofino switch and 100 gig on Elvo U280 FPGA. And the figure on the right shows the latency overhead of Planter, meaning the latency on top of normal forwarding. And this overhead is in the order of nanosecond to tens of nanoseconds on hardware targets, and less than a millisecond on software target. And Planter has already been extended to support several deployment scenarios. In hybrid deployment, a small in-network machine learning model is deployed on a network device, and a large model at the backend. Only high-confidence decisions are made inside the network, and others are sent to the backend. And in this manner, the same machine learning accuracy is achieved as very large machine learning model, but will also reduce the server load by 70%. In distributed deployment, we disaggregate a large in-network machine learning model into small components and distribute it across multiple programmable network devices, allowing to further scale in network machine learning models. The last, federated learning, is enabled for privacy-preserving scenarios with Planter-generated model deployed on multiple places. And also, as there is data skew over time, runtime model update is supported and hitless. Early adopters have already used Planter in a range of different use cases. And for example, the network functions include load balancing using Q-learning and IoT traffic classification. Cybersecurity applications include e-commerce bot traffic detection and smart grid for data injection detection. And even the finance-related use case include predicting future stock price movement and transaction fraud detection. In summary, in-network machine learning can be efficiently mapped to programmable network devices, achieving high machine learning performance within low resource overheads, fitting on different programmable network devices, and especially the commodity one. And there are many new and more applications to explore using in-network machine learning. And Planter enables you to easily develop and deploy your own solutions by extending the current framework. And in the end, we would like to invite you to try Planter today and change the future of networking. And thanks, and I'm happy to take your questions.
Okay, there's time for questions if there are any. If not, that's okay. Okay, here's a question. Yep.
Hi, thank you very much. It was a great talk. I have a general question. So how does in-network machine learning inference compare to doing machine learning inference on the edge? I would imagine like doing on edge servers will achieve like equally low latency and will support more general models. Could you comment on what are the differences between these two approaches? Thank you.
Thanks for the question. And I think in terms of latency, in-network machine learning allows you to reduce the hops. For example, if you want to use edge servers, it means that you need to firstly forward to the server. But before you forward to the server, there are already network devices. And if you can deploy in-network machine learning on this device, then which means you have lower latency. And this latency reduction can be hundreds of nanoseconds to even microseconds. And compared to the more general models, like in-network machine learning already support around a dozen machine learning models. And for this model, for a reasonable size, it has the same inference performance of server implementations. For example, using scikit-learn standard library. But if you want to try some larger model, for example, the deep neural network, not like 3 layers, 4 layers, but tens or hundreds of layers, then definitely the server-based solution using GPU probably will be a better solution.
Okay, any other questions? Oh, yeah, we have time for one more question.
Hi, Kalika from NICTech, Thailand. Thank you for the talk. I'm just curious about how can the in-network can check the integrity of each model. Like you have to divide and run in different network components. So how can they have like a check which one is the model? This one.
May I ask if my understanding is correct, it's related to the distributed deployment of a large machine learning model across different programmable network devices? Yes, we do have some design. For example, we use ILP to allow that the distributed deployed components have integrity. So it is a constraint in this ILP problem. So we also have a paper related to the distributed deployment on Connex last year. So probably you can check that paper, which is named DINK. So it's the fourth paper toward distributed in-network computing. Thanks.
Okay, we can thank the speaker.
Thanks.
Yeah.